the most ancient way to keep track of a solar day is to use a sundial. So as the sun moves around in the sky, the shadow cast by this object here would move around the dial, indicating the time of the day. And when the sun is transiting, the shadow would be perfectly aligned with the object, so it would appear right in the back here, and you know that it's noon. So a solar day would be defined from noon, when the shadow is in the middle, to the next noon, when the shadow is in the middle again. And we know this is usually 24 hours on average. And here's the catch. The length of the solar day varies from over the course of the year. There are two reasons for this. The first one is that the orbit of the Earth around the Sun is not a circle, but an ellipse, which means that the speed of the Earth as it travels around the Sun varies from place to place. So it is faster at perihelion and slower at aphelion. Now you do remember the difference between the solar day and the sidereal day. The solar day is the time from noon to noon again, which means that you must have the same orientation relative to the sun. If you're facing the sun, which means this is noon, the sun is transiting, is at the highest, and then you do a full rotation that you give you the sidereal day, you must rotate an extra degree to face the sun again, and that is your solar day. Except that that angle of 1 degree varies. If you're traveling close to the perihelion, you're moving faster, which means that for the same time interval, you will actually travel an angle greater than 1 degree, which also means that the solar day will be longer because you have to turn a bigger angle. The rotation must be more than 1 degree. So that extra angle you travel is more than 1 degree, the day is longer. Same way, if you are at aphelion, the angle is smaller because you're moving more slowly, and the solar day tend to be shorter than average near the aphelion. So there is this kind of sinusoidal function for the average length of the day over the course of the year. The other reason why the apparent solar time fluctuates over the course of the year has to do with the obliquity of the ecliptic. Now, this diagram here that gives us the difference between sidereal day and solar day assumes that the north axis is actually out of the page, assumes no obliquity. So now let's imagine that we are in the spring or fall equinox. The Earth is oriented like this. Now let's picture that the sun is actually out of the page, so in front of you here. The direction of motion around the sun is horizontal. So we imagine that the revolution of the sun, the Earth, so the ecliptic, is parallel to the XY plane here, horizontal, right? While the axis of rotation of the Earth is diagonal. The 1 degree that the Earth has to revolve around the sun is horizontal. Yet, the rotation of the Earth is not horizontal, is diagonal. In other words, you must cover a 1 degree angle horizontally, but you're moving diagonally, which means that the angle that you actually have to turn is greater than 1 degree. And you can see that if you are in a winter or summer solstice, then the axis is actually aligned, and in that case, the amount of rotation that the Earth has to complete to catch up with its motion around the sun is, in fact, closer to 1 degree. So there is a difference in the angle that you rotate because the difference in orientation due to the obliquity, and that creates a fluctuation that varies twice a year. So from equinox to solstice, from equinox to solstice. So this sine function, you have it twice over the course of the year. And now the result is a combination of the two factors. So how big is this discrepancy? It can be up to 1 minute per day, maximum. It's not a lot, but it accumulates. So let's say currently the apparent solar time is shorter than average, so it kind of gets ahead of the average, then every day you lag by 1 minute. After 10 days, the difference is 10 minutes. After 20 days, the difference is 20 minutes. So this accumulated delay or lag between the solar day on average and the current solar day or apparent solar day builds up. So what is a fluctuation of 1 minute per day builds up to 15 or even 20 minutes difference in some extreme situations. And it's very complex because it's the sum of two sine functions. So fortunately for us, there is a graph that gives us the answer right away, so we don't need to do any math. Before we discuss the equation, let's make sure we understand what we mean by mean solar time. So this would mean that this time is based on the average over the course of the year, so that on average, on your sundial, if you follow this clock, on average the sun will be transiting at noon. Sometimes it will be transiting earlier, sometimes it will be transiting later, but on average it will transit at noon over the course of the year. And the duration of the day on average will be 24 hours. This is solar time. This is the graph that would represent the difference between the apparent solar time, so the day-to-day, versus the mean solar time when you average out over the year. So these are three lines here. One large sine function that represents the discrepancy due to the elliptical orbit of the Earth. The faster frequency, so twice a year, represents the effect due to the obliquity of the ecliptic. And then this is in red, the combined effect. So this is the accumulated difference between the apparent solar time and the mean solar time. So it's apparent minus mean. So, for example, the date is November 1st. November 1st, the difference is roughly 16 minutes. So, the apparent solar time minus the mean solar time is positive 16 minutes. So, let's say it is noon. It is 12 p.m. according to your mean solar time. What time is it according to your sundial, which records the apparent solar time? Well, apparent minus mean equal plus 16 minutes. So, apparent minus 12 p.m. equal 16 minutes. So you add 16 minutes there, and the apparent time would be equal to 12:06 p.m. So even though your electronic clock, which you set up to your mean solar time, says this is noon, the sun has already passed the midpoint in your sundial. So your sundial and your clock don't agree. Oh, and I just picked up a mistake I made. This should be 16 minutes, not 6 minutes. I'm sure you noticed that as well. The mean solar time is based on your local coordinates, which means that as you travel around the globe, around the Earth, and your longitude changes, the mean solar time will also change. So for example, if you live in Montreal, which has a longitude of 70 degrees west, and you travel eastward, then let's say 72 or 71 degrees west, then at this location, the sun has gone further in its path. So if right now the sun is transiting in Montreal, then the sun has already transited past a point to the east of Montreal. That's because the sun will go from east to west as the Earth rotates. And similarly, places located further west will have an earlier mean solar time at the same time as we do in Montreal. So for example, right now, if the sun is transiting, it is still morning in Vancouver. The sun has not yet reached the transiting point in Vancouver. So every single longitude in the world will have its own unique measurement of mean solar time, which means that as you're traveling eastward or westward, you must be continuously adjusting your clock to match the mean solar time of your current location. Of course, this is not practical. That's why we divided the Earth into 24 reference meridians, which are all the hour meridians that separate the Earth into time zones. These time zones are 15 degrees apart, as you know, and your location will match the mean solar time of the nearest reference meridian. So for Montreal, that would be 75 degrees west. Every 15 degree, and the 0 degree will be Greenwich. So here this is 60, this is 45, this is 30, this is 15, and Greenwich will be here. There is a difference of 1, 2, 3, 4, 5 time zones with Greenwich. So in Montreal, which should have the local time, the solar time of a location at 73 degrees west, we're actually using the mean solar time of the 75 degree west meridian, which means that there is a difference between the standard time. So this is what we call the standard time, the time that we currently use based on the 75 degree west, which we call the Eastern Standard Time in Montreal. Then there is a discrepancy with 2 degrees. The discrepancy is 4 minutes per degree times 2 degrees, so that's 8 minutes. Our mean solar time in Montreal is 8 minutes away from the standard time that we use in our everyday clock. Is it 10 minutes earlier or 10 minutes later? We are further to the east. So the sun will pass through Montreal before passing through the 75 degree west meridian. So the mean solar time, the local mean solar time of Montreal is 8 minutes later, higher than the mean solar time of the 75th west meridian or standard time. So the Eastern, for example, standard time would be 2 p.m. Then to find the mean solar time in Montreal, we would have to add 8 minutes. So it will be 2:08. And so this is an important also distinction. By the way, to determine which time zone you belong to, you have to look for the nearest reference meridian. So if the separation between the reference meridians is 15 degrees, then you can go half of 15 degrees on each side, which means 7.5 degree east or 7.5 degree west of this reference meridian. So most locations in that range would fall with the East Standard Time. So now we also have the Universal Standard Time. This is the time at Greenwich, and this is the reference for Earth. So for the Eastern Standard Time, we are five time zones west, so 5 time zones earlier. So in other words, if the sun is passing through the Greenwich Standard Time and it is noon at Greenwich, then it is 5 hours earlier in Montreal. The sun has not yet reached Montreal, which means that the Eastern Standard Time will be equal to the Universal Standard Time minus 5 hours. And for every 15 degree, you adjust by 1 hour.